Welcome back to the deep dive. Today, we are not just skimming the surface of microbiology. We are going deep into the gut. We're looking at a specific group of bacteria that I kind of like to call the twisted cousins of the gastrointestinal tract.
Twisted cousins is actually a very, very good way to put it. Geometrically accurate, even. We are talking about the curved gram-negative rods.
Exactly. We are finally leaving the world of the straight rods, your classic E. coli, your salmonella, and we're looking at the ones that have a bit of a spiral to them.
A bit of a curve.
Yeah. And specifically, we are going to be dissecting Chapter 28 of Murray's Medical Microbiology.
The 9th edition. That's our main framework for today.
It is, and because we want to make sure you are absolutely bulletproof for your exams, we're also pulling in those really high-yield descriptive pearls from Chapter 17 of Jowet's.
It's the perfect pairing, really.
Yeah.
Murray gives us that solid structural spine, the pathogenesis, the clinical progression, all of that.
Right.
And then Jowet's comes in and gives us those vivid visual anchors, the things you need to recognize in, like a split second on a board exam question.
Okay, so here's the roadmap for the next hour. We have a very clear mission today. It's to distinguish between two major generas that, on the surface, look pretty similar, but they act very, very differently.
Completely differently. We've got Campylobacter on one side.
And Helicobacter on the other.
Right. Two bacteria, both curved, both gram-negative, both motile. But their whole life strategy, their entire approach to infection is just diametrically opposed.
I've been trying to come up with a mental model for this to keep them separate in my head.
Okay.
And I see Campylobacter as the hit-and-run arsonist. It breaks in, it lights a massive fire. We're talking huge inflammation, bloody diarrhea, and then for the most part, it gets chased out by the immune system.
That is a perfect analogy, which makes Helicobacter the
silent squatter.
The silent squatter, yes.
Right. It moves into the stomach, probably the most hostile piece of real estate in the entire body, and it sets up shop. It renovates the place to its liking and then stays there, sometimes for decades, causing this slow, chronic damage over a lifetime.
And that really is the core distinction we're going to hammer home today. It's acute invasion versus chronic persistence.
Okay, so what's the big theme? The idea we should keep in mind through all of this.
The theme I want everyone to keep in the front of their mind is this. Shape dictates niche.
Shape dictates niche.
There is a reason these bugs are curved. There is a very specific evolutionary reason they have tails, or flagella. They are biomechanically engineered to drill through mucus.
I love that. Shape dictates niche. Okay, let's start with our arsonist then. Let's open the dossier on Campylobacter.
Let's do it. Campylobacter. The name itself is a clue. It comes from the Greek campylos,
which means
curved.
So a curved rod. Now, Murray makes a big point right out of the gate that this isn't some kind of, rare, obscure pathogen you might see once in your career.
Not at all. It is arguably the most common cause of bacterial gastroenteritis in both the developed and the developing world. I mean, we're talking millions upon millions of cases annually.
Wow.
If you have a patient come in with acute bacterial diarrhea, statistically speaking, Campylobacter has to be very, very high on your differential diagnosis.
Okay, but here's the paradox. If it's so incredibly common, why is it so notoriously hard to grow in the lab? I remember reading that for the longest time, we didn't even really know it was there because we just couldn't culture it with our standard methods.
That's because Campylobacter is what we call fastidious.
Picky.
Incredibly picky about its environment. If you take a stool sample and you just streak it on your standard McConkey agar and leave it on the bench in normal room air, you will never find it.
Why not?
It'll be dead within hours.
Okay, so let's put on our pathologist hats for a second. We're in the lab. What are the specific demands that this little diva of a bacterium makes?
Okay, first and foremost, let's talk about the atmosphere. Campylobacter is microaerophilic.
Microaerophilic, so small air-loving.
Exactly. It needs oxygen to live. It's not an anaerobe, but it only wants oxygen at very low levels. We're talking specifically 5 to 7%.
And what's in the air we're breathing right now?
About 21% oxygen. Yeah. And if you expose Campylobacter to that, it's completely toxic to it.
Why? What's the mechanism?
The bacteria just lack robust antioxidant defenses. They don't have high levels of enzymes like superoxide dismutase or catalase to handle that much oxidative stress.
Yeah.
So it essentially just burns up. It can't cope.
So it's a Goldilocks bug. It needs a little bit of oxygen to breathe, but too much will kill it.
Precisely. And that's not all. It also needs high carbon dioxide, somewhere around 5 to 10%.
Okay, so how did labs figure this out in the old days?
Well, back in the day, labs used to use something called a candle jar. It's pretty clever. They'd put the Petri dishes inside a big glass jar, light a candle, and then seal the lid.
And the candle flame would.
It would burn up some of the oxygen, lowering the concentration, and at the same time release CO2.
Yeah.
It created that perfect, microaerophilic environment.
That is some seriously old school microbiology. I love it. But there's another condition, isn't there? One that's even more high yield for exams, specifically for Campylobacter jejuni.
Yes.
And this one involves temperature.
This is probably the most critical differentiator. Campylobacter jejuni is thermophilic.
Thermophilic. Heat-loving.
It grows best at 42 degrees Celsius.
42 degrees, that's hot. I mean, normal human body temperature is 37. Pretty much all other human pathogens, your E. coli, your staph, your strep, they're all optimized for 37. Why does Campylobacter want it so hot?
To answer that, you have to look at the reservoir. You have to ask, where does Campylobacter live when it's not making humans miserable?
Poultry. Chickens, turkeys.
Exactly. And birds, because they have a much higher basal metabolic rate, also have a higher basal body temperature than we do. A chicken's normal internal temperature is roughly
42 degrees Celsius.
42 degrees Celsius.
So the bacteria quite literally evolved to thrive in the gut of a chicken.
Precisely. And we can actually use that evolutionary adaptation against it in the lab. If you get a stool sample, it's a soup of thousands of different bacteria.
Right, a total mess.
So to isolate Campylobacter, you take that sample, put it on a special plate, and stick it in an incubator set to 42 degrees.
Then the heat kills off the competition.
It inhibits the E. coli and all the other normal gut flora.
Yeah.
The Campylobacter, it thinks it's back home in the chicken, and it just grows like crazy.
I actually have a mnemonic for this. That's how I always remember it.
Let's hear it.
Campy loves the campfire.
That's excellent. I'm stealing that.
Campy for Campylobacter.
Right.
Campfire, because it's hot 42 degrees, it helps you remember both the temperature and, by extension, the reservoir.
And that reservoir is the absolute key to the epidemiology. This is a zoonotic disease through and through.
So you get it from animals?
You get it from handling raw poultry, from eating undercooked chicken, and sometimes from things like unpasteurized milk or contaminated water.
It is the classic summer barbecue food poisoning story.
Yeah, it really is.
But I want to get visual again. Okay, so we've done it. We've grown it at 42 degrees in our low oxygen jar. We do a gram stain. What am I looking at under the microscope?
You're looking for very small, very thin gram-negative rods.
Yeah.
But the key is they aren't straight. They have this very characteristic curvature to them.
And Javits has a very specific, very famous phrase for this, doesn't it?
It does. This is the money phrase. Javits describes them as often appearing in pairs, shaped like seagull wings.
Seagull wings. Okay, I can picture that.
Yeah, imagine you're drawing a simple bird in the landscape. Just that little M shape or V shape in the sky.
Got it.
That is what Campylobacter looks like. Or sometimes you'll see it described as comma-shaped.
Okay, so they look like seagulls. Are they just sitting still on the slide?
Oh, never. If you're lucky enough to look at a wet mount, meaning the bacteria are still alive in a drop of liquid, you'll see they have this very specific, very characteristic movement. They have a polar flagellum, which means a single tail at one or sometimes both ends. And they use this tail to move with a darting motility.
Darting. Not tumbling, not swimming, but darting. Like they're just shooting across the slide.
Exactly. It's not a gentle tumble. It's a rapid, driven, purposeful motion. And this brings us right back to our central theme.
Shape dictates niche.
Right. Why do they need to dart? Why do they need to be curved?
It has to be about getting through the mucus layer in the gut.
Exactly. The intestine is lined with this thick, viscous layer of mucus. A straight rod, like E. coli, might just get stuck, get bogged down.
But a corkscrew shape.
A corkscrew or a curved shape can drill through that medium much more efficiently. That shape and that darting motility allow them to swim right through the mucus to reach their target. The epithelial cells lining the gut.
Okay, so the arsonist has arrived. You ate the undercooked chicken. The bacteria have now made it to the intestine. But wait, what about the stomach?
Good point. We should definitely mention the gastric acid barrier.
Right, how do they survive that?
Well, the truth is, Campylobacter is actually quite sensitive to acid. It really doesn't like a pH of 2. So, under normal circumstances, you need a pretty high infectious dose to get sick.
So you have to eat a lot of bacteria.
Maybe 10,000 organisms, something like that.
Yeah.
Enough to overwhelm the stomach acid and get a critical number of survivors into the small intestine to set up an infection.
But that threshold can change, can't it?
Oh, it drops dramatically if the acid barrier is gone.
You mean like in a patient who's taking heartburn medication?
Exactly. If a patient is taking proton pump inhibitors, PPIs for reflux, or even just a lot of antacids,
Hmm.
or if they have a condition like equihydraria where they don't produce much acid,
Then the infectious dose plummets.
it becomes much, much easier to get infected. A much smaller number of bacteria can cause disease.
That's a great clinical pearl. So if you see a patient on chronic PPIs, their risk for this kind of food poisoning is significantly higher. Okay, so the bacteria makes it through the stomach, it drills through the mucus, and it reaches the jejunum, hence the name C. jejuni. What happens next? Why do we get bloody diarrhea?
This is where that arsonist label you came up with fits so perfectly. Campylobacter is invasive.
It doesn't just sit on the surface.
No, it doesn't just sit on the surface and secrete a toxin like, say, Vibrio cholerae. It physically penetrates the mucus layer and invades the epithelial cells of the jejunum, the ileum, and the colon.
It literally breaks into the house.
It breaks in, and it starts multiplying inside the cells. And this, as you can imagine, triggers a massive immune alarm. The host cells start screaming for help.
How do they do that?
They release pro-inflammatory cytokines, and the big one here is interleukin-8, or IL-8.
And IL-8 is the dinner bell for neutrophils.
It's the ultimate neutrophil magnet. So neutrophils and monocytes just rush to the site of invasion, and the result is significant tissue destruction.
So the lining of the gut gets damaged.
Very damaged. The mucosa becomes edematous, swollen, ulcerated, and friable, meaning it bleeds easily. If you were to look at a biopsy, you'd see something called crypt abscesses.
Which are?
Little pockets of pus, dead neutrophils, deep down in the intestinal glands. It's a sign of intense, acute inflammation.
And all of that tissue destruction is why you see blood in the stool.
Correct. Vibrio gives you watery diarrhea because it just messes with fluid transport. Campylobacter gives you bloody diarrhea because it is physically destroying the lining of the gut.
Yeah.
When you look at the stool under a microscope, you'll see red blood cells and white blood cells, leukocytes.
And symptomatically, this must feel awful.
It's miserable. Patients get a high fever, malaise, and severe abdominal pain. In fact, the pain can sometimes be so focused in the right lower quadrant that it perfectly mimics acute appendicitis.
Pseudoappendicitis.
Exactly. It's not uncommon. We've seen cases where surgeons take a patient to the OR expecting to find a burst appendix, and the appendix is totally fine. But the terminal ileum right next to it is bright red, angry, and inflamed from the Campylobacter infection.
So that's a classic clinical vignette to watch out for. Right lower quadrant pain, fever, bloody stools. Don't just jump to the conclusion that it's the appendix.
You have to ask about their diet. It could be the chicken they ate last week.
Right. Now, typically this is self-limited, isn't it?
Yes, for the most part. The diarrhea lasts about a week, the immune system eventually wins the battle, and the arsonist gets chased out of town.
But for a few unlucky patients, the nightmare is just beginning.
This is where we get into the sequelae, the post-infectious complications. And the big one, the one you absolutely have to know, is Guillain-Barré syndrome.
GBS, this is incredibly high yield.
It is. Campylobacter is the most common antecedent infection linked to Guillain-Barré. It's estimated that somewhere around 30 to 40% of all GBS cases are triggered by a recent Campylobacter infection.
We have to break down the mechanism here because this is both fascinating and, frankly, terrifying. How does a simple stomach bug end up causing you to become paralyzed?
It's a tragic, elegant case of what we call molecular mimicry.
Molecular mimicry.
It turns out that the outer coat of certain strains of Campylobacter, specifically a strain called serotype O.1, contains these complex sugar structures called lipoligosaccharides, or LOS.
LOS.
And the really unfortunate part is that chemically, the sugars on these LOS molecules look almost identical to the gangliosides that are found on the surface of our own peripheral nerves.
Gangliosides like GM1, for example?
Exactly like GM1. So your immune system does what it's supposed to do. It recognizes the Campylobacter LOS as foreign, and it produces a whole bunch of antibodies, IgG, IgM, to go and destroy the bacteria.
So the immune system builds a weapon specifically designed to kill the bacteria.
And it works beautifully. The infection is cleared. The bacteria are killed.
Yeah.
But now you have all of these antibodies still circulating in your blood.
And as they float past your peripheral nerves,
They see the gangliosides.
and because they look the same as the bacterial LOS,
The antibodies lock on. They mistake your own nerves for the bacteria they were built to fight. They bind to the myelin sheath, or sometimes to the axon itself, and they trigger complement activation. They start destroying the insulation around your nerves.
it's a case of friendly fire.
The ultimate friendly fire incident. And this leads to widespread demyelination. The nerve signals can't get through.
And clinically, this presents as what?
It presents as an ascending paralysis. The weakness typically starts in the feet and the hands, and then progressively moves up the body.
And if it gets to the diaphragm?
You can't breathe. You require mechanical ventilation. It is a life-threatening medical emergency.
Wow. And all because the bacteria wore a disguise that happened to look just like our own nerve cells.
That is the essence of molecular mimicry.
There is one other sequela mentioned in Murray, right? Something called reactive arthritis.
Yes. This is more common in patients who have a specific gene, HLA-B27. It's not a direct infection of the joint. It's a sterile inflammation of the joints, usually the knees and ankles. That happens a few weeks after the diarrhea has resolved.
Right. It's often part of a classic triad.
Yes. Arthritis, urethritis, and conjunctivitis. The old mnemonic is can't see, can't pee, can't climb a tree.
Okay, so to recap C. jejuni, it gives us bloody diarrhea. It looks like seagulls. It grows at 42 degrees, and it can cause GBS. But there's a black sheep in the family, isn't there? A cousin that doesn't really play by the same rules.
That would be Campylobacter fetus.
C. fetus.
Yeah.
Even the name sounds more serious.
And it behaves very differently. While C. jejuni is out causing diarrhea in otherwise healthy people, C. fetus is a true opportunist.
Who does it target?
It targets the immunocompromised, the elderly, and people with serious underlying conditions like liver disease or diabetes.
And crucially, it doesn't just stay in the gut.
No. And this is the key difference you have to grasp. C. jejuni generally stays localized to the gut because it is very sensitive to the complement system in our blood. If it happens to get into the bloodstream, our serum kills it pretty effectively.
But C. fetus has a superpower.
It is a suit of armor. It's encapsulated with a very specific surface protein called the S protein.
S for superpower.
S for surface, technically, but I like superpower. It works. This S protein creates this protective lattice structure all over the bacterium that physically prevents a critical complement protein, C3b, from binding.
And if C3b can't bind,
then the immune system can't opsonize the bacteria. The phagocytes, the cells that are supposed to eat bacteria, can't grab onto it. And so C. fetus becomes resistant to serum killing.
So it can survive and even thrive in the blood.
Exactly. It causes bacteremia, septicemia, and it can seed distant organs. It can cause septic thrombophlebitis, endocarditis, even meningitis.
So if I have a frail, elderly patient with a high fever and positive blood cultures showing a curved gram-negative rod, I should not be thinking jejuni.
No, your mind should immediately go to fetus. Jejuni is the gut arsonist. Fetus is the systemic invader of the vulnerable.
Perfect. Before we leave Campylobacter for good, let's just wrap up the diagnosis. We talked about the culture conditions, 42 degrees, microaerophilic. Is there a simple biochemical test to confirm it's C. jejuni?
Yes, the hippurate hydrolysis test.
Hippurate.
This is the definitive lab differentiator, and it's a favorite for exams. Campylobacter jejuni produces an enzyme called hippuricase. It can hydrolyze hippurate. It is hippurate positive.
And the other Campylobacters?
Almost all other medically relevant species, including C. fetus and C. coli, are hippurate negative.
So, seagull wings plus 42 degrees plus hippurate positive equals C. jejuni.
You've got it. That's the trifecta.
All right, let's shift gears. We're leaving the inflamed intestine behind. We're traveling upstream past the duodenum into the stomach. It is time to meet our silent squatter.
Helicobacter pylori.
You know, the story of H. pylori is genuinely one of my favorites in all of medicine. It's a story of scientific rebellion.
It really is. I mean, up until the early 1980s, it was absolute unquestioned dogma in medicine that the stomach was sterile.
Right. The pH is 1 to 2. It's a vat of hydrochloric acid.
The consensus was that nothing could possibly live in there.
So if you had ulcers, doctors told you it was because you were too stressed, or you ate spicy food, or you had a classic type A personality.
That was the teaching. And then these two researchers from Australia, Barry Marshall and Robin Warren, started seeing these little curved bacteria in biopsies from their ulcer patients.
And nobody believed them?
Nobody. The medical establishment thought they were crazy. They faced outright ridicule.
So Barry Marshall did something legendary.
He did. He took a beaker full of H. pylori culture, and he drank it.
That is the ultimate hold my beer moment in the history of science.
It really is. He literally infected himself. And sure enough, within a week, he was vomiting, he had terrible halitosis, and when they did an endoscopy, his biopsy showed acute gastritis teeming with H. pylori. He proved Koch's postulates on himself.
And they eventually won the Nobel Prize for it. But the question remains, and this is the deep dive part, how does it do it? How on earth does a bacterium survive in battery acid?
It brings its own personal chemistry set, the single most important virulence factor for H. pylori. The one thing it cannot live without is the enzyme urease.
Urease. Okay, let's really unpack the chemistry here. What is it doing?
So the stomach naturally contains some urea. It's a metabolic waste product from protein breakdown. H. pylori produces massive, truly enormous amounts of this urease enzyme, which grabs that urea.
And does what with it?
It hydrolyzes it. It splits it into two things, carbon dioxide and ammonia.
And ammonia NH3, that's a base.
It is a strong base. So I want you to picture the bacterium. It's sitting there in this acid bath, and it is constantly pumping out this enzyme, which in turn is creating a constant cloud of ammonia right around its body.
So it's neutralizing the acid in its own immediate vicinity.
Exactly. It creates this localized alkaline spacesuit or a little protective halo. The general stomach lumen might be at pH 2, but inside that ammonia cloud, the pH is much closer to neutral.
And that allows it to survive just long enough to do what?
To activate its motility, to get out of the acid.
And here's where the shape comes in again, that corkscrew shape.
Right. It has what we call Lophotrichus flagella, a whole tuft of tails at one end.
Yeah.
It uses that spiral shape and those powerful tails to literally drill its way into the thick mucus layer that lines the stomach wall.
And why does it want to go into the mucus?
Because there's a natural pH gradient. The stomach lumen is incredibly acidic, but the surface of the epithelial cells right underneath that mucus blanket is actually near neutral. The mucus acts as a buffer.
So H. pylori swims away from the acid through the mucus and attaches to the epithelial cells where it's safe.
The urease buys it time, and the shape and motility get it to safety.
But there's a kicker, isn't there? That ammonia cloud isn't just a shield.
No, it's a weapon too. Ammonia itself is directly toxic to our epithelial cells. It causes mucosal injury. So the very mechanism the bacteria uses to survive is also what starts the process of tissue damage.
So it's sitting there, attached to the stomach lining. It's not invading the blood like C. fetus. It's just squatting.
It is a non-invasive surface colonizer, but it is incredibly chemically aggressive.
Yeah.
It releases a whole suite of enzymes, mucinase, to break down the mucus and thin the stomach's natural protection, phospholipase, and then it brings out the heavy hitter toxins.
Okay, let's talk about the toxins. This is the arsenal. Murray highlights two really major ones, Vaffe and Kekai.
Let's start with VECA. That stands for vacuolating cytotoxin A.
The name pretty much gives it away.
It does. It causes the formation of vacuoles, these large empty pockets, inside the host's epithelial cells. It essentially turns the cell cytoplasm into Swiss cheese.
And what does that do to the cell?
It disrupts the mitochondria, it messes with energy production, and it induces apoptosis or programmed cell death. All of this damages the barrier function of the stomach lining.
And then there's KEGA. This one sounds even more sinister.
KEGA stands for cytotoxin-associated gene A, and this one is fascinating because of how it gets into the cell. H. pylori uses a molecular machine called a tight IV secretion system.
I always pictured this as a microscopic hypodermic needle.
That is a perfect visualization. The bacterium literally builds a syringe that punches through the host cell membrane and injects the KEGA protein directly into the cytoplasm of our cells.
That is incredible. It's like a biological Trojan horse, but it's injecting its own proteins directly into our cells.
And once that KEGA protein is inside, it just wreaks havoc. It completely messes with the cell's cytoskeleton, changing the cell's shape. Pathologists call it the hummingbird phenotype.
Okay, but what's the most important thing it does?
It hijacks cell signaling pathways to trigger massive inflammation. It essentially forces the cell to start pumping out that same cytokine we talked about before, IL-8, which calls in an army of neutrophils.
And chronic inflammation over years and decades. That's the recipe for cancer.
Precisely. Strains of H. pylori that are KEGA positive are known to be much more virulent and are very strongly associated with a much higher risk of developing gastric cancer.
So let's trace the clinical timeline of this silent squatter. You usually get infected as a kid, right?
Yes. Transmission is typically fecal-oral or oral-oral. In many developing countries, the vast majority of children are infected by the time they're 10 years old.
So phase 1 is acute gastritis. Maybe some nausea, some vomiting, but it's often so mild that it's missed entirely.
That's right. Then you move into phase 2, chronic gastritis. And this is where the location of the infection really matters.
This is a subtle but really high-yield point, isn't it? The outcome depends on where in the stomach the bacteria decides to set up shop.
Absolutely. Let's say it stays mainly in the antrum, which is the bottom part of the stomach.
Okay, what happens then?
If it colonizes the antrum, it tends to interfere with the feedback loops. specifically the release of a hormone called somatostatin that normally tell the stomach to turn off acid production.
So you lose the off switch.
You lose the off switch. The result is hyperacidity. You end up making way too much acid.
And all of that extra acid then gets dumped into the first part of the small intestine.
The duodenum, and it just burns the duodenal lining, causing duodenal ulcers. This is why 90 to 95% of all patients with duodenal ulcers are infected with H. pylori. It is the #1 cause, by far.
But what if the infection doesn't stay in the antrum? What if it spreads to the whole stomach, a condition called pangastritis?
Then you get the exact opposite effect. The chronic, widespread inflammation eventually destroys the parietal cells, the very cells that make the acid. You get what's called gastric atrophy.
So your acid levels drop.
You can develop a chlorhydria, a lack of acid.
Yeah.
But because you're losing all of your normal glandular tissue and it's being replaced by fibrosis or even intestinal-type cells, a process called metaplasia, the risk of cancer just skyrockets.
And this is the direct pathway to gastric adenocarcinoma.
It is.
And we should probably state this very clearly. H. pylori is a known carcinogen.
It is. The World Health Organization classifies it as a Class I carcinogen, right up there with asbestos and smoking. It is the single strongest risk factor for developing gastric cancer in the world.
But there is another very strange type of cancer it causes, one that is unique because of how we treat it. MALT lymphoma.
Yes. MALT stands for mucosa-associated lymphoid tissue. Now, under normal circumstances, your stomach does not have lymphoid tissue. It's not supposed to be a lymph node.
Okay.
But because H. pylori causes such an intense, chronic, decades-long inflammatory response, the immune system eventually decides to set up a forward operating base right there in the stomach wall.
So it actually builds lymphoid follicles in the stomach lining to fight the infection.
Exactly. You get this massive proliferation of B cells, all trying to make antibodies to fight the bacteria. And eventually, after years of this constant stimulation, one of those B cells can acquire a mutation and turn malignant.
And that is a MALT lymphoma.
That's it, a B-cell lymphoma of the stomach.
And here's where we get to the magic trick.
The magic trick is that in its early stages, this cancer is often still completely dependent on the antigenic stimulation from the bacteria to continue growing. The bacteria are literally the fuel for the fire.
So if you kill the bacteria,
you starve the cancer. For early-stage gastric multi-lymphoma, the first-line treatment is not chemotherapy, it's not radiation, it's a course of antibiotics.
You're kidding.
No, you eradicate the H. pylori, and in a majority of cases, the tumor simply regresses and disappears on its own.
That is just mind-blowing, the idea that you can cure cancer with amoxicillin.
It's one of the most remarkable relationships in all of oncology. Truly.
So given all of this, the ulcers, the cancer, we absolutely have to be able to diagnose this bug accurately. How do we find the silent squatter?
We have two main approaches, invasive or non-invasive. The invasive way is to do an endoscopy. You go down with a camera, you see the inflamed stomach lining, and you take a biopsy.
And what do you do with that biopsy tissue?
You could do two things. You can look at it under a microscope, usually with a special Warden-Starry silver stain. That's the gold standard for actually visualizing the bacteria.
Okay.
Or you can do the rapid urease test, which is often called the CLO test.
How does that one work?
It's very clever. You take the little piece of biopsy tissue and you drop it into a gel that contains two things, urea and a pH indicator.
And if H. pylori is there?
Its powerful urease enzyme will immediately start splitting the urea into ammonia. The ammonia, being a base, raises the pH of the gel, and the indicator dye turns from yellow to a bright pink or red.
And it happens fast.
Very fast, often within an hour or two.
Okay, but what if I don't want a camera put down my throat? What are the non-invasive options?
Then we use the urea breath test, or UBT, and this is just beautiful, elegant science.
Walk us through it.
The patient comes in and drinks a small amount of a special solution containing urea. But this isn't just any urea. It's been labeled with a specific trackable carbon isotope, usually carbon-13, which is non-radioactive.
So they drink the labeled urea?
And if, and this is the key, if and only if they have H. pylori in their stomach, that urease enzyme will immediately break the urea down. The labeled carbon atom gets turned into labeled carbon dioxide gas.
And that CO2 is a gas.
So it's absorbed across the stomach, lining into the blood, it travels to the lungs, and then the patient breathes it out.
You capture their breath.
We capture their breath in a little bag and we analyze it with a mass spectrometer. If we find that specific isotope of carbon, we know with very high certainty that the urease enzyme is active in their stomach.
Which means the bug is there.
Which means the bug is there, It has extremely high sensitivity and specificity.
And it's also the best way to test if the treatment worked.
Exactly. It's the test of choice for test of cure. After you've treated the patient with antibiotics, you wait a few weeks, and then you repeat the breath test to make sure the bug is well and truly gone.
What about blood tests? I see serology offered sometimes.
You have to be very, very careful with serology. A blood test is just looking for IgG antibodies against H. pylori.
What's the problem with that?
The problem is that those antibodies can stay in your blood for years, sometimes for life, even long after the infection has been successfully cleared.
So a positive antibody test doesn't actually tell me if I'm sick right now.
It just tells you that you had the bug at some point in your life. It has a very low positive predictive value for active current infection. You should not use serology to diagnose active disease if you can possibly avoid it.
Stick to the breath test or the stool antigen test.
Absolutely.
Okay, so we found it. Now we have to kill it. And this sounds tricky because of the acid environment.
It is. The acid can degrade many common antibiotics like clarithromycin, and the bacteria are hiding deep within that protective mucus layer. So we need a multi-pronged attack.
The basic strategy is acid suppression plus antibiotics.
Exactly. You must raise the stomach pH first. This does two things. It lets the antibiotics work more effectively, and it allows the ulcer itself to begin healing. So we always include a proton pump inhibitor, a PPI.
And then we add the antibiotics.
The classic regimen for many years was triple therapy. That was a PPI plus 2 antibiotics, clarithromycin and amoxicillin.
But I hear there are problems with that now.
There are. Clarithromycin resistance rates are rising dramatically. So in many places, we now have to move straight to quadruple therapy.
Which is?
That's a PPI plus bismuth plus 2 different antibiotics, usually tetracycline and metronidazole.
Bismuth? You mean like in Pepto-Bismol?
The very same. Bismuth is a fascinating addition. It actually coats the base of the ulcer, creating a physical barrier, but it also has direct antimicrobial properties. It helps to lytolize the bacteria. It's like bringing in the heavy artillery.
So we really hit it with everything we've got. Now, before we summarize everything, there's a quick mention in the outline of something called enterohepatic helicobacters, the other guys.
Right, just a quick note on those for completeness. There are other species, like Helicobacter cineae and H. phanelliae, and the key thing to know is that these do not live in the stomach. They live in the intestine and biliary tract.
And who gets these infections?
They are classic opportunistic pathogens. You primarily see them in immunocompromised individuals, specifically in men who have sex with men and in patients with advanced HIV.
And what do they cause?
They can cause proctocolitis, but they can also get into the blood and cause bacteremia and cellulitis.
Okay, so there's a little mental bookmark for that specific patient demographic.
Correct. Stomach is pylori. Intestine in an immunocompromised man could be one of these other guys.
Perfect. Okay. We have covered a massive amount of ground. Let's try to bring it all together now in a comparative summary.
The curved rod lineup.
Let's do it. First, Campylobacter jejuni, the arsonist.
For campy, you should think. Poultry reservoir. Thermophilic, so it loves 42 degrees Celsius. It's invasive. It causes a bloody inflammatory diarrhea. And you always have to remember that looming autoimmune shadow of Guillain-Barré syndrome.
Got it. Second, Helicobacter pylori, the squatter.
For helico, you have to think. Urease positive. That's the key to survival, the ammonia cloud. Its niche is the stomach. It causes chronic inflammation that leads to ulcers, both duodenal and gastric, and over the long term, cancer, both carcinoma and multilymphoma.
And just to round it out, let's briefly contrast them with their third cousin, Vibrio.
Right, Vibrio is also a curved rod, but it's different. It grows in alkaline media on TCBS agar. It causes a profuse, watery rice water stool because it's toxin-mediated and non-invasive, and you get it from contaminated shellfish or water.
So to boil it down to a tweet, campy equals blood plus fever plus chicken.
Helico equals pain plus ulcers plus urease.
And Vibrio equals water plus dehydration plus shellfish.
That is the high-yield differentiation you need for your exams.
And the why behind it all comes back to our theme.
Shape dictates niche. Campy darts through the gut mucus to invade and cause acute disease. Helico corkscrews through the gastric mucus to persist and cause chronic disease.
Excellent. That was a perfect summary. Now it is time to test our listeners. We are going to do a rapid-fire single best answer recall.
Let's see if the key concepts really stuck.
Okay, here's how it works. I'm going to read a clinical vignette or a mechanism-based question. I'll pause for just a few seconds. That's your time at home to say the answer out loud. Then our expert will give you the correct answer and, most importantly, the why. Ready?
Ready?
Question 1. A 24-year-old male presents with ascending muscle weakness and paralysis that started in his lower extremities. 2 weeks prior, he had experienced an episode of fever and bloody diarrhea after eating at a poultry barbecue. These neurological symptoms are caused by antibodies against the bacteria cross-reacting with which specific host structure?
The answer is gangliosides, specifically GM1 gangliosides on the surface of peripheral nerves. The reasoning is that this is a classic presentation of Guillain-Barré syndrome triggered by Campylobacter jejuni. The mechanism is molecular mimicry, where the bacterial lipoligosaccharides, or LOS, structurally resemble our own human gangliosides, leading to a devastating autoimmune attack on the nerves.
Question 2. You are a microbiologist attempting to isolate the causative agent from a stool sample that contains both erythrocytes and leukocytes. You decide to use a selective medium containing antibiotics, and you place the culture in a microaerophilic jar. To specifically select for the most likely pathogen, what temperature should you set the incubator to?
The answer is 42 degrees Celsius. The reasoning is that the pathogen is almost certainly Campylobacter jejuni. You have to remember our mnemonic. Campy loves the campfire. It is thermophilic because it's adapted to the higher body temperature of birds. Setting the incubator to this higher temperature inhibits the growth of other normal enteric flora like E. coli while allowing the Campylobacter to thrive.
Question 3. Helicobacter pylori is famous for its ability to colonize the extremely acidic environment of the stomach. Which bacterial enzyme is absolutely essential for the initial neutralization of gastric acid in the immediate vicinity of the organism, allowing it to survive?
The answer is urease. The reasoning is that urease hydrolyzes urea, which is present in the stomach, into ammonia and CO2. The ammonia is a strong base that effectively neutralizes the gastric acid, creating a protective alkaline cloud around the bacteria that permits its initial survival and subsequent colonization of the mucus layer.
Question 4. An 80-year-old female with a history of leukemia presents to the ER with fever, chills, and hypotension. Blood cultures are drawn and reveal a curved gram-negative rod. Further analysis shows that the bacteria is encapsulated with a special S protein that prevents the binding of C3b. What is the most likely pathogen?
The answer is Campylobacter fetus. The reasoning here is that, unlike C. jejuni, C. fetus is a systemic pathogen that preys on immunocompromised hosts. The key is that S protein capsule, which confers serum resistance by blocking complement opsonization via C3b. This allows it to survive in the bloodstream and cause bacteremia and sepsis.
Question 5. A 55-year-old man undergoes an endoscopy for chronic dyspepsia and is diagnosed with an early-stage gastric MALT lymphoma. A biopsy confirms the presence of H. pylori. What is the most appropriate initial management step for this patient's cancer?
The answer is eradication of the H. pylori infection, using a combination of antibiotics and a PPI. The reasoning is that MALT lymphoma is often driven by the constant antigenic stimulation of the chronic H. pylori infection. By eradicating the bacteria, you remove that growth signal, which frequently leads to complete tumor regression without any need for chemotherapy or radiation.
Question 6. A patient undergoes a gastric biopsy. The tissue is immediately placed in a urea-rich gel that contains a pH indicator. The gel turns a bright pink color within 60 minutes. This color change is due to the bacterial production of which specific chemical?
The answer is ammonia. The reasoning is that this describes the rapid urease test, or CLO test. The urease enzyme from H. pylori splits the urea in the gel into ammonia. Ammonia is alkaline, which raises the pH of the gel and causes the colorimetric indicator to change color, confirming the presence of the organism.
And our final question, question 7. A lab is trying to speciate a Campylobacter isolate. Which single biochemical test is most useful for differentiating Campylobacter jejuni from other common Campylobacter species like C. coli and C. fetus?
The answer is the Hyperiot hydrolysis test. The reasoning is that C. jejuni is characteristically Hyperiot positive, meaning it possesses the epiricase enzyme. Most other clinically relevant Campylobacter species are Hyperiot negative. This is a classic board exam differentiator.
So how did you do? If you stumbled on any of those, I highly recommend you open up Murray chapter 28 tonight and look specifically at that summary of clinically significant organisms table. It's a fantastic cheat sheet.
And I'd add, make sure you can draw out the mechanism of the urea breath test. Understanding how the isotopes work really helps to lock that concept in.
Before we sign off, I want to leave you with a final provocative thought to chew on. We spent this whole hour talking about H. pylori as a clear-cut villain. It causes ulcers, it causes cancer, we want it gone.
But biology is rarely ever that simple.
Exactly. There's this growing concept called the disappearing microbiome. As we have quite ruthlessly eradicated H. pylori in the Western world with antibiotics and better hygiene, the rates of gastric cancer and peptic ulcer disease have dropped significantly. And that's a huge win.
However, over that exact same time period, the rates of esophageal adenocarcinoma and gastroesophageal reflux disease, GERD, have absolutely skyrocketed.
Why would that be?
Well, the leading theory is that H. pylori, by chronically reducing the overall acidity of the stomach, especially in those cases of gastritis, might have actually been protecting the esophagus from acid damage.
So it might be an ancestral commensal, a frenemy that we've co-evolved with for over 60,000 years to help regulate our gastric physiology.
It's a real possibility. By evicting the silent squatter, we might be solving one very serious problem downstairs in the stomach, but inadvertently creating a brand new problem upstairs in the esophagus.
It really raises the question, is a microbe strictly a pathogen, or is its role entirely context-dependent? The answer is likely far more complex than we thought.
Something to ponder.
It is. So keep asking why. Keep those rods curved and keep your knowledge straight.
Goodbye, everyone.